SwayamPrabha. Digital India. Educated India.
Okay, so welcome back. This is the last part of the module, properties. So we were discussing about the property table. Okay, now we are going to discuss equation of state. Basically, equation of state is nothing but which relates PVT in some analytical form, which allows one to make use of the equations to solve problems. So the simplest and the best known equation of state is basically the ideal gas equation of state. And it was around 1662 when Robert Boyle found out that the pressure proportional to 1 by specific volume. Okay, and that led to the development of PV is equal to RT. Okay, so what is R here? R apparently is a constant, proportionally constant, and this turns out to be the gas constant. Okay, this R is in the units of kilojoules per Kelvin, and this R values is dependent on the substance. Now you can divide R, you can write this expression in the different form. You can write this expression as this, and you can make it PV MRT. Okay, so this is the traditional ideal gas equation of state. You can also write in terms of moles. Okay, so we know that moles, 1 mole contains Avogadro number of molecules, or 1 mole is equivalent to a molecular weight of a substance, okay, in grams. So if we convert this in moles, then essentially you are going to get this kind of expression, okay, where N is the mass, okay, divided by molecular weight, and therefore your gas constants get modified and it's written as RU. So this is the universal gas constant here, okay, and the universal gas constant is related to gas constant in this form. So we can write this expression or this expression depending on whether you have information of mass or the moles. So as I mentioned already that you mass and moles are connected by this, so you can write this in terms of moles or in terms of mass. You can also write in a simpler form where you divide N both sides such that this is PV by N RU, and this particular expression becomes molar property or molar volume. Earlier we have written this as RT, where this was specific volume. Now this would be P RUT. So this is another form of writing ideal gas expression. So as I said, this is a per unit mass basis, this is per unit mole basis. Now the real gas behave as an ideal gas only at extremely low density, which essentially means low pressure. Okay, and you can approximate it. There is a region where this ideal gas behavior is seen, but it's not valid for all the conditions, and that's what we need to develop new equation of state. So that's something which we are going to study later. Okay, so let's take an example how we make use of this ideal gas equations. So the example is that you have measured the gauge pressure of an automobile tire before a trip. It was 210 kilopascal. After you undergone the trip, the pressure become 220 kilopascal at a location where the atmospheric pressure is 95 kilopascal. So we have to find out the temperature in the tire after the trip before. So what we are assuming is that the volume of the tire is constant, and what is given is the air temperature before the trip was 258 degrees Celsius. So what we are going to do, the first thing is we are going to consider air as an ideal gas, and then you find out the pressure. Let's say before the trip is P1. Okay, this would be P atmosphere, P plus P gauge, okay, which was before it was 210 plus 95 kilopascal. Then you have P2. In a similar way, P2 is going to be 220 plus 95 kilopascal. So you are aware of the pressure based on this information. Now if you are using ideal gas, so we know ideal gas is PV. Whether you take based on mass, whether you take based on moles, because of the fact the volume remains constant, the mass is going to be constant, because mass is also constant, is a closed system, and as well as your number of moles is going to be constant. Okay, so whether we take let's say MRT in this form, then we can write before the trip information. Okay, so this is going to be T1 MR. Okay, this should be same as T2 because this is constant. Now V1 and V2 is constant, which essentially means I should be able to find T2 as P2 by P1 T1, and this is how we are going to solve this problem by replacing P1 and P2 by this value, and T1 we know 258 degrees Celsius. So this is the way to solve simple problems such as by making use of gas approximating to ideal gas equation of state. Okay, so what about other vapors, other gases such as the water vapor? Is it an ideal gas? So let's take a look of this table. This is a TV plot, and this is just a specific region of vapor plus liquid. Again, this is your saturated liquid and this is your saturated vapor line. Okay, and this is your critical point. Now what you see is these values here. These values are nothing but the percentage of error from the steam table, from the table which we have used earlier, the error with respect to if we use for example ideal gas. So ideal gas values, the corresponding ideal gas let's say specific value, and how much it deviates from the steam table values. In terms of percentage of error, this is a representation. Now 0 indicates that it is perfectly representable. Ideal gas approximation is pretty good in this case, okay, which is of course this region we have defined, okay, and this is also at low pressure. So this, look at this is at very low pressure. These are low pressure regions, okay, and as you go at a higher pressure, the values starts deviating. So this ideal gas approximation doesn't work. Near the critical point, 56.2% is extremely large, and that's where we understand that at the pressure below 10 kilopascal, water vapor can treat as an ideal gas. You can see 10 kilopascal here, okay. This region is pretty much can be represented by ideal gas, and regardless of its temperature. So that means even if you increase the temperature, this is extremely high temperature, okay. High temperature, low pressure. So high temperature, low pressure, the ideal gas approximation works. On the other hand, if you increase the pressure, the deviation is quite large and hence it's not going to work. Near the critical point, of course, is not going to work. So in case of an air conditioning application, can we make use of ideal gas approximation? And the answer is yes. Why? Because the pressure of air conditioning applications are very low. However, you cannot make use of ideal gas approximation for the case of steam power plant because it usually operates at high pressure. Now it's nice to make use of ideal gas equation of state, but it has a limited application because it's suitable only for a certain range, as we have already seen, high temperature, low pressure region. But we desire to have equation of state which works in a wide range of applications. Now, so ideal gas is easy and convenient to use, but it deviates from the real gas properties for certain condition, and this is why we need to also look at certain parameters which identify this kind of deviation, and this parameter or factor which we call is compressibility factor, okay, and this is the factor that accounts for the deviation of real gas from ideal gas behavior at a given temperature and pressure. So we can write in this form that Z is nothing but PV by RT, okay. So for the case of ideal gas, Z is 1, okay, and any deviation from Z equal to 1 is a representation of deviation from the real gas properties or from the ideal gas behavior. So real gas can have greater than 1, can have equal to 1 values or less than 1. So if it deviates from Z equal to 1, the real gas actually deviates from the ideal gas behavior. So this is quite useful in many applications which we make use of it. Now we know that gases behave as an ideal gas at low density, that is low pressure and high temperature. We have already illustrated this based on the graph which we have used, which essentially means as pressure is low, the real gas behaves like ideal gas. But what is the criteria for low pressure and a high temperature? So you take an example, let's say minus 100 degrees Celsius. Is this temperature low or high? Okay, and that's where it depends on the substance. For water it is certainly low, but for nitrogen and other gases is very, very high. Why? Because for nitrogen, for example, the critical temperature is around minus 140 degrees Celsius. So this temperature is much higher. Thus, the pressure or temperature of a gas is high or low relative to the critical temperature or pressure. So if you look at any plot, okay, you have to look at any plot like this. So temperature is higher only when is above the critical point. So you can have many different substance which can have different kind of plots. So I can draw it here. So you may have like this for one substance, you may have another substance like this, another substance, all in the same thermodynamic variable, and this temperature here may be high for this substance, but this may be low for other substance. So the criteria for low and high temperature is with relative to the critical temperature or pressure, and this is something quite interesting because if you take various different gases and take the properties and reduce it with their critical property, it turns out that lot many gases which are of similar nature such as methane, propane, ethane, they start behaving similarly in the reduced plots. So they have remarkably same property if you reduce the temperature and pressure with their critical properties. So in some sense, which means that you have taken out the characteristic nature of the molecules by dividing the property with their critical properties. So this is what we say as a principle of corresponding state, and this is the basis of that, where we make use of this reduced pressure, reduced temperature, which is nothing but the pressure divided by the critical pressure of the substance, and same with the reduced temperature. And you can also calculate VR. Okay. So now based on this, you would be surprised to see that Z versus PR for many different gases, they have almost similar plots, and that's what it allowed us to calculate or come up with this kind of plots, such as what we call it here is compressibility chart. So the compressibility chart contains Z as a function of reduced PR of many different gases. Okay, these are all gases, and so you can see these symbols represent that they all fall in the same curve, and this line here is TR. So essentially this line has a specific reduced temperature values. So what does it mean? So if you take let's say methane and propane, so methane and let's say propane, okay, and you take a value of reduced pressure at certain point, and for a specific TR values, you can find out the Z value. Okay. So Z for methane will be same as Z for propane, as long as the PR and TR for both the system is same. So based on this, you can do calculations and obtain the Z values and find out the deviation from the ideality. Z also can be determined from the knowledge of PR and VR. That's what we said. So VR can be used to calculate. So the figure A15 in the appendix of the test book contains more complicated, more rigorous kind of plot, which actually is more of based on what I showed in the previous slide, and made use of some rigorous fitting, and this is the plot or the chart which we commonly use. So this is for the low pressure regime. So here you have a PR, you have again a Z, and then you have your TR, and as well as they have also included VR, the reduced volume. We can make use of this particular chart to solve certain problems. Now, as I said, the desire to develop equation of state has been prominent and still is ongoing effort for industrial applications, because what we desire is to come up with equations which we can solve in the computers, make instead of using tables all the time. But we can realize that these are very difficult job because of the nature of the PVT surfaces and the complicated nature of the molecules. That's why many specific equation of state has been developed. It started way back by van der Waals, which wanted to change the ideal gas equation of state by including the nature of the intermolecular forces and as well as the size of the molecule. So it was in 1873 by van der Waal, which came up with this modification of ideal gas equation. Okay, and what he did was introduced these terms which represent specific nature of the molecules. So molecules do have volume, and hence the volume of the system reduces because certain volume is occupied by the molecules. So that's why the effective volume is less. And what about this term? Now in case of an ideal gas, it doesn't have any interaction. Ideal gas molecule can just pass through each other. So they can just pass through each other without colliding. On the other hand, due to the interaction between the molecules, they will collide. So essentially you can think from the number of collision on the wall of the container, due to the interaction the number of collision will reduce. So you can think of this equation of development is that you can write this ideal gas equation of state in this form, and when you include the volume of the molecules, you have to reduce the volume here, right? And further the pressure gets reduced due to the interaction of the molecules by this term. Okay, and this particular expression can be written in this way. So this is a contribution, or rather the reduction in the pressure due to the intermolecular interactions. So that was the van der Waal equation of state. Now you can find out these particular variables A and B by taking help from the nature of the curve going through the critical point. So at critical point, for a given temperature or for critical temperature, it undergoes inflection. The curve undergoes inflection, hence the first derivative of pressure with respect to volume at T critical should be 0, and as well as the second derivative should be 0. Okay, and thus based on this you can calculate A and B in terms of TR and PR. Okay, so this is how it will come. So this model is used for a long time, but is not very accurate for many different regions of the phase. Okay, and thus there has been many different developments by introducing more variables in the equation. So for example, this is Bethe-Bridgman equation of state. It has 5 constants, and then you have a Benedict-Webb-Rubin equation which has 8 constants, and naturally this is fitted to the experimental values, and then you have obtained these variables. Okay, not all of them have a very sound theoretical reasons for having these terms. Okay, this is mainly derived from the van der Waal and later on added various different terms. Now the one which has a very sound theoretical background is virial equation of state. So virial equation of state has this ideal gas term, and then the other term is added, which is a contribution to the interaction between 2 particles, interaction due to 3 particle or due to 4 particle cluster and so forth, because you can consider the gas phase to be made of this different component, and this the virial coefficient is just a function of temperature. So let's see how it fares when you put it in a real scenario for the real gas. This is a nitrogen, and this is again temperature versus molar volume in this case plot, and we have plotted for various different equations of state, and the values which is represented here is an error, just like we had earlier for water, and clearly some of them does very good job. So the summary is here. It turns out that the Bennett-Webb-Rubins are pretty good, okay, for accurate for density, okay, quite high up till 2.5 times the critical density. This Strobich is quite useful for the computer calculations. Virial based equation of state, though it's quite useful, but it has limited utility because the virial coefficients are not known for many systems. Only few virial coefficients are known, up till 4 to 5. But if you want to increase the accuracy of virial equation of state, we have to include more number of terms. So thus we see from this small example that complex equation of state is required to capture the PVT properties or diagram of simple systems, simple gases. Okay, with that let's go to the summary of this particular module. So we started with the definition of pure substance, phases of pure substance. We went through the phase change process. We described the compressed liquid, saturated liquid, superheated and systems. Then we went to the property diagram and the phase change and how to describe the phase change on the property diagram. We also illustrated the use of property tables by doing some examples, and finally we ended today with equation of state, starting with the ideal gas equation of state leading to other complicated equation of state. Okay, so with that, this is the end of this particular chapter, and next we are going to look at the energy analysis of a closed system.